Okay, so Bohr's model of the atom. We had just finished Rutherford's. Rutherford's that wasn't stable because it has electrons accelerating around the nucleus, accelerating because they're changing direction. And we know that any charged particle that accelerates gives off energy. And so if it's losing energy, that would be energy of motion, kinetic, which means it's losing speed. And if it's losing speed, it means gravity is going to be stronger than it can handle, and it's going to get pulled in. It's going to spiral into the center. So this model would only be stable for 1/100 millionth of a second, and as it collapsed, it would give off a continuous spectrum of light. Obviously, we don't see a whole bunch of rainbows popping up and zipping all over the place where atoms are collapsing every 100th millionth of a second. So this can't be the model. Also, if it was, all the atoms would have disappeared by now. So Niels Bohr comes along. So Rutherford's model was 1911. Niels Bohr proposes a model in 1913 that takes Rutherford's model and tries to make it more stable. So he bases his atom on Rutherford's model, okay, in an attempt to improve it. And he also bases his model on the hydrogen atom and its behavior. So he looks just at hydrogen, he suggests a model for hydrogen, and then he assumes that if it works for hydrogen, it'll work for others. So he makes a few assumptions. So he has like 13 propositions, and one of them isn't that it's based on the hydrogen atom. That's just like the lead-in line. So he has these following assumptions. Assumption number one is that the electrons move, and you have these notes, or they're on the group file for you. But assumption number one is that the electrons move in a circular orbit. Okay, so here's the nucleus, and so he is agreeing with Rutherford that electrons are moving in a circular orbit around the nucleus. Assumption number two is that since electromagnetic energy is quantized, remember that was Einstein and Planck that used that earlier, he's saying that all energy is. So it's not just electromagnetic energy that's quantized, all energy is. And so that electrons can only gain and lose energy in fixed amounts. So if these are our energy levels, he's saying an electron can only jump up by gaining a packet of energy in a fixed amount, and when it falls back down, it's going to lose that packet of energy. So electrons can only gain and lose energy in fixed amounts. This is assumption 2. His assumption 3 is that electrons of hydrogen can only occupy orbits of fixed energies and no other. So in other words, if this is the hydrogen atom, an electron can be here, it can be here, it can be here, maybe here, in the different orbits, right? Or if you want, I could do it around the nucleus, but it can't be anywhere in between, right? So these are just one section of these orbits around the nucleus. So an electron can be anywhere in this orbit or anywhere in this orbit, but it can't be somewhere in between them. It can only be in the particular orbits there's only certain orbits that are allowed. Okay, so that's number 3. Number 4 is that electrons can jump from lower to higher orbits by absorbing a quantum of energy. The same amount of energy is released when it falls back down. So in number 2, it was that electrons could only gain and lose energy in fixed amounts. And number 4, he says, so if an electron wants to go from a lower orbit to a higher orbit, it needs to absorb energy. And when it falls from the higher orbit to the lower orbit, it's going to release that same amount of energy, that quantum of energy, that packet of energy. Okay? And it's a fixed amount. So today, tomorrow, the next day, and if an electron is in this lower orbit, and wants to jump up, it needs the same amount of energy each day to jump up into the next orbit. Okay? Number 5 is that each orbit corresponds to a certain amount of energy, with the ones closest to the nucleus being the lowest energy. So, right? So maybe here the electron has an energy of a certain amount, the next one it's set. So like maybe this is 4 electron volts, and then this is 8 electron volts, and then this might be 9 electron volts. So there's set amounts, okay? That's number 5. Number 6, each orbit is a stationary state called an energy level. A stationary state called an energy level. So we will now start to refer to these orbits as energy levels. And in chemistry, in grade 11, you probably talked about like what energy level the electron is in. So these orbits are now, we're going to refer to them as energy levels. Number 7, these energy levels are numbered starting with the lowest. So this one down here is the lowest. It's n equals 1. This one would be n equals 2, n equals 3, n equals 4. And if we look around the orbit, this would be the 1, this would be the 2. So 1 is the lowest, closest to the nucleus. And these numbers, these n equals, they are the principal quantum number. Principal quantum number. Okay? When an electron is in its lowest state, down here at the n equals 1, his number 8 statement assumption is that when an electron is in its lowest state, it's said to be in the ground state. So the lowest state is the ground state. Okay? And that's n equals 1. And remember, this is for hydrogen. So there's only one electron in hydrogen. So if you were doing aluminum or something, it would have more electrons and they wouldn't all be in the n equals 1. But for hydrogen, there's only one and it's in the n equals 1. His number 9 is that if an electron is in any level above the ground state, so if this little electron that's in the n equals 1 absorbs this quantum of energy and jumps up to here, then we say it is in an excited state. And again, remember, this is for hydrogen. Other ones would have electrons in the n equals 2 level because they'd have more electrons than hydrogen does. But if a hydrogen electron is in an n equals 2 level, it is in an excited state. It's absorbed quantum of energy and it has jumped up. Okay? Number 10 says that excitation happens when an incident photon, when a photon comes in, and that photon's energy corresponds to the difference in the energies between the two energy levels. Okay? So this little electron down here can only jump up if the difference in these two energy levels, the difference in the energy is equal to the energy in the photon. Okay, so excitation, jumping up, happens when an incident photon's energy corresponds exactly to the difference in the energy levels. So if I say, like, so if it could go from 1 to 3 if the photon matches from n equals, or sorry, for n equals 1 to n equals 2 if the photon exactly matches that. But if the photon's bigger, it could jump straight up to 3 if it exactly matches that. Or it could jump straight up to 4 if it exactly matches that. But it has to match exactly the difference between two of the levels. It doesn't have to be two consecutive levels, but it has to be the difference between two of the levels. Okay? So that's his number 10, and it leads to an equation in number 11, which says the energy of the photon has to equal, and remember energy of the photon is HF, and that has to equal the energy of the final level minus the energy of the initial. Remember, change in is always final minus initial. Okay? So if this ends up being a positive, then it means it jumped up. If it's a negative, then it means the electron dropped down. So if you get a positive answer here, it means this photon was absorbed and the electron jumped from a higher level to a lower level. If you get a negative answer when you do the math here, the electron is released as it drops down. We'll come back to this tomorrow. Your homework tonight will not be on this because I want to finish Bohr's model first. So your homework tonight is the rest of the multiple choice sheet. which I think is like 9, if you haven't done it, 19 to 35, and the practice assignment. Okay?